So once again, this is where our syllabus brings us. We've already covered 3.2.1 to recapitulate basic principles of green chemistry and the 12 principles of green chemistry. Then we also discussed a large number of waste minimization techniques that are possible to be applied at the chemist stage. They can be applied at the engineer stage, the production stage, and so on and so forth, right? And the principal text that we are going to be following, the reference that we are going to be following for this chapter is a book by Lancaster. I've already emailed the book to all of you, so you can refer to the relevant chapters as we were discussing moving ahead. Okay, and the second part in the unit 3.2.2 is on catalysis and green chemistry, involving three different types of catalysts, green catalysts. One of them is phase transfer catalyst, biocatalysts, and photocatalysis. So we've discussed the mechanism of action of a phase transfer catalyst, which happens to be a quaternary ammonium, phosphonium, or a sulfonium salt. And these salts have a tendency to equilibrate between the aqueous and the organic phases. And because they have a tendency to distribute between both, they will enrich the nucleophile in the organic phase where the substrate is going to be present in major concentration, because most organic substrates are not water soluble, right? So we looked at the principles of phase transfer catalysis and also a certain number of examples where it can be employed. We also looked at biocatalysts, majorly enzymes. But apart from enzymes, you can also be using live organisms to bring about the same sort of catalysis. And the last one, photocatalysis. So some semiconductor material like very popularly used is titanium dioxide, TiO2, because it offers a good band gap between the conduction and the valence bands, which is in the range of the semiconductor material. And if you apply the right electromagnetic radiation, the electron can jump from the valence band to the conduction band, resulting in an free electron that can move in the conduction band, and there will be holes that will be generated in the valence band. And these holes and electrons will then be capable of doing a large number of redox catalysis. So you have applications of these catalysts in that particular redox phenomena. What we are going to be looking at today is 3.2.4, that is alternative energy sources for initiation and execution of chemical reaction. And we are going to in particular see how microwave and sonochemistry can be applied as an alternative energy source for doing chemical reactions. Okay. So clean chemical synthesis can be done using alternative reaction methods, and the alternative reaction methods can either come from an alternative energy source like that of ultrasound, solar energy, or microwave. As a part of our syllabi, we'll be focusing on ultrasound and microwave. And also there can be an alternative reaction media that can be offered that can make your reaction on the whole green. So you could do a solvent-free synthesis. So you're just mixing two raw materials by themselves without having the need to add any solvent. So you could do a solvent-free synthesis. You could use water as a solvent because water is the greenest solvent possible. You could use supercritical fluids, and we have supercritical fluid as one of the topic in the syllabi that requires to be covered as a part of 3.2.3. We'll come to that eventually. You can also use ionic liquids or deep eutectic solvents. Even ionic liquids need to be covered as a part of the syllabi. Or you could use certain other green solvents like polyethylene glycol, etc. Okay, and of course, the easiest is to do either a solvent-free or a solid-supported kind of a synthesis. And we will see some solid-supported reactions being done in conjunction with either microwave kind of a setup. Okay, let's come to microwave-assisted organic synthesis. First, we are looking at what are the characteristics of microwaves. Microwaves are electromagnetic radiations, but just that their wavelengths are in the range of 1 millimeter to 1 meter. So in that particular region of wavelengths in the entire broad electromagnetic spectrum range, you call the radiations as microwave radiations. And these radiations, despite having a large energy values associated with individual wavelengths, starting all the way from 1 millimeter to 1 meter. There is some restriction to the use of microwave for either commercial purposes like a microwave reactor, or the domestic purposes of microwave oven. Now that is because most of the communication channels which happen between radars, etc., are also operating in the same frequency region. Okay, so the only frequency that is available for doing microwave assisted organic reactions or some domestic microwave purpose is 2.45 gigahertz, right? So that's the only frequency available. And microwave reactors are different as compared to microwave ovens, and we'll see how exactly they are different. I mean, these are the type of microwave reactors that are commonly employed to perform microwave assisted reactions, whereas our traditional microwaves have a very different kind of a design, and they are meant to do some altogether different purpose. And we'll see why exactly we require so sophisticated or a very specialized kind of an instrumental design so as to do microwave assisted organic synthesis. Now, before we move ahead and start looking at principles of microwave reaction, we have to look at what are the advantages that microwave assisted synthesis offers. So it offers the advantage of rapid reaction. Now that is something that is not very far-fetched, because we know that food gets cooked much faster in a domestic microwave as compared to conventional heating. So it doesn't come as a surprise that most organic reactions are also completed in less than few minutes, as against refluxing them for a number of hours by conventional heating. So you would see such kind of comparisons whereby conventional heating requires about 2 to 3 hours of reflux, whereas microwave reaction requires only about 2 to 3 minutes of microwave irradiation. So rapid reactions is an advantage. High purity of products, because most of the time microwave offers complete conversion of the starting material to the product due to the high efficient design in terms of supplying the energy to the reactant. So since efficiently the energy is supplied to the reactant, all of the reactant gets converted into the product. Now that means that unreacted reactant problem is not going to be much of an issue when you do microwave assisted synthesis, and therefore your products are going to be of high purity. You also have improved yields because you achieve the desired activation energy for all the molecules so that they can get converted into the products. So often the yields of microwave synthesis is superior as compared to conventional reactions. It's simplified and improved synthetic procedure also offers a very big advantage. And there is a wide usable range of temperature that you can probe while you're doing microwave assisted reactions, and there is a higher energy efficient design in terms of use of microwave. Okay, let's first look at the principles of microwave heating, and then we'll come to what is the difference between a commercial microwave reactor versus that of a domestic microwave oven, and why exactly do you need to build up the kind of instrumental differences between the two, because they are predefined to perform two very different functions, right? So the mechanism of heating through microwave can either be due to one of these three different mechanisms. Okay, one can be either there is a dipolar polarization of the molecule, of a polar molecule that is being irradiated with microwave radiations, or if you have ions in solution or ions as a part of the medium that you're trying to heat through microwave radiations, then there will be some conduction or mobility of ions in the presence of electromagnetic radiation, which results in heating. Or there is also another phenomena called as dielectric loss. So even due to dielectric loss, there will be some microwave heating that will be observed, right? Now let's come to the first one, dipolar polarization. Now all of us know that if at all we keep a glass of water inside the microwave, in about 2 minutes, water becomes piping hot, right? So there is some mechanism that might be operating, or some interaction between microwave radiations and water is making it go to such high temperatures over a very, very short span of time. So what is the mechanism involved? In water, there are no ions, right? I mean, if you're putting pure water, pure distilled water inside the microwave, there are no ions in it. So what is the cause of heating basically? Okay, so this dipolar polarization can be represented by a GIF like this. what this animation is trying to tell you is, as the electromagnetic radiations are traveling through the medium, they will induce some rotational energy changes in the molecule, which is polar, right? And these are some things that you've also come across in parallel with certain quantum mechanical derivations that you do for rotational spectra. So whenever there is polarity in the molecule, because of irradiation with microwave radiations, which is just right to go from a lower rotational level to a higher rotational level, there'll be rapid rotations that will be set up in these polar molecules. These rotations will lead to some friction. So as two molecules tend to rotate, they tend to collide or brush over one another. And as they start moving over one another, there is some friction that is generated. And this friction at the molecular level leads to a large amount of heat that is released. So this is one of the fundamental basis of microwave heating. So what happens in a microwave heating is microwave radiations travel into a medium that is polar. Because of the polarity, there are some rapid rotations that are set up. These rotations will lead to friction between multiple molecules that are trying to rotate at the same time. The friction is the cause of the characteristic outcome of microwave, which is microwave heating, right? Now, this kind of a change is called as dipolar polarization. Now, you'd be wondering, why doesn't this happen at frequencies which are higher than the microwave radiation, as well as frequencies that are lower? So if you talk about electromagnetic radiation, and if I talk about 1 millimeter to 1 meter wavelength being present over here, then all electromagnetic radiations below 1 millimeter as the wavelength would fall under lower frequency or higher energy electromagnetic radiation. And at the same time, all the electromagnetic radiations which have greater than 1 meter as the wavelength would fall under the lower frequency or a lower energy electromagnetic radiation, right? So let's first discuss what happens when you have electromagnetic radiations which are more energetic than microwave. Okay, so as of now, if you look at the GIF carefully, the animation carefully, you see that the crest and the troughs are spaced out, and they are coming out at a very, very low frequency, allowing for the water molecule to perform those rotational motions. Imagine the frequency of light to be extremely high. So that means there is a large change in the wavelength happening over a very small period of time. So even before the crest is felt by the molecule, the trough comes in contact with the molecule. So the molecule is not able to make any rotational motion because the change in the phase of the electromagnetic radiation is much faster than the time required to perform some rotation. Do you get that? So that is the reason why all the radiations which are more energetic than microwave are incapable of bringing about the characteristic heating associated with microwave. Okay, that's point number one. Point number two, what happens in cases of radiations which are less energetic than microwave? That means whose wavelength is greater than 1 meter. In such cases, the change in the angle of rotation is so slow, okay, that it cannot bring about an appreciable increase in the temperature of the system. So microwave radiations have their wavelengths at a very, very characteristic position, which is just appropriate to bring about rotations in molecules that are polar. And these rotations can lead to a very high degree of localized heating that is possible by using microwave, right? That is in case your medium consists of polar molecules that is not consisting of ions. What happens if your molecule consists of ions? If your molecule has ions, then these ions by themselves will start migrating under the influence of an electrical field. Okay, that's the most characteristic type of interaction that you will see between ions and electromagnetic radiation. Okay, now these translational motions being induced on the ions will result in them colliding with one another. These collisions result in a large amount of heat as energy that gets released when these ions come in collision with one another. So that's how ions tend to get heated, if at all ions are present in solution. There's also another phenomena called as dielectric loss. So what is dielectric loss? Whenever electromagnetic radiations strike matter, they promote the matter to one of its excited energy levels. We've already come across a Jablonski diagram which talks about multiple electronic energy levels. Within electronic energy levels, there are multiple vibrational energy levels. Within vibrational energy levels, there are some rotational energy levels, and so on and so forth, right? So each time there is electromagnetic radiation striking the matter, there will be some uh, exchange of energy by which the matter itself will go to a higher energy state. But the matter cannot remain at the higher energy state forever, right? It has to come back down into the ground state. And as it does so, it starts releasing a little bit of heat. So there is thermal deactivation of molecules that get activated due to interaction with electromagnetic radiation. And we call this as dielectric loss. This is what makes the temperature become uniform for a certain medium that is absorbing electromagnetic radiation. Okay, so that is the principle behind microwave heating, basically. So three mechanisms. One of them is dipolar polarization, which is observed in polar molecules. Most typically, the example of water can be given for uh, microwave heating by dipolar polarization as the mechanism. Then you can have heating up of various ions, like say, for example, if you add sodium fluoride to silica, or sodium bisulfite to alumina, then sodium fluoride and sodium bisulfite will offer ionic medium that can result in microwave heating due to conduction. So there is some movement or migration of these ions under the influence of electrical field of the electromagnetic radiation. And due to their movement and collision, they release a large amount of heat that comes out. So that is due to ions. And the third one is due to dielectric loss. And dielectric loss is just that the matter goes to an excited energy level by interacting with electromagnetic radiation. Since it can't sustain an excited state forever, it has to come back to the ground state. And as it does so, there is thermal deactivation. So there is some amount of heat that is getting released each time a molecule from the excited state comes back to the ground state. So how is this different from conventional heating? In conventional heating, as you can see here, the container has to be heated first, right? So you put your container on top of a flame, and the flame has to first heat the container. The container would then result in heating the solvent. The solvent will then transfer its energy to the substrate, which has to undergo some reaction. And you're familiar with the 10% law in thermodynamics, right? So energy or heat transfer is never quantitative. So there is almost 90% of loss that happens for every transfer of heat that takes place. So only effectively 10% of the heat is going into heating up of the surface of the container, say for example. And 10% of that heat is going into heating up the solvent. Only 10% of the heat from the solvent is going into activating the reactants to perform reaction. And that's why conventional heating is not energy efficient, because a large amount of heat is just going waste into the environment, basically, right? On the other hand, in a microwave heating, what is happening? Most of the times for microwave reactions, or even in microwave ovens, we use microwave safe cookware, right? So the container by itself does not absorb microwave radiations at all. But the microwave radiations penetrate the container, go into the molecule. At the molecular level, it leads to heating, which can take place due to one of the three mechanisms that we've discussed. So microwave heating is most often described as inside out kind of heating, because it's not the container getting hot, then the heat being transferred from the container to the solvent and so on. It's more so the electromagnetic radiations penetrating and going into that location where heating is desired. And from the inside, there is an outward heating mechanism that is found in case of use of microwave. On the other hand, conventional heating is outside in kind of heating. So you have to keep going into the layers so that you can reach the target molecule, which happens to be your substrate, right? Okay, before we go to applications of microwave assisted synthesis, I just wanted to quickly run you by the differences between a commercial microwave reactor in which we can do organic reactions versus that of a typical microwave oven that we see in our homes, basically. So the design is very, very different, and the cost also of a microwave reactor, which is domestic, versus that which can be used in performing microwave reactions, there's a huge disparity. So SEM is one of the companies which makes microwave reactors, okay? And the reason why you require specialized reactors to do microwave reaction is uh, whenever you've opened a microwave oven, you see a turntable, right? So that turntable is where your container goes, and the container keeps rotating. And if you've observed carefully on one of the uh, surfaces of the inside of the microwave, you have some perforations, and there is a lamp, from which there is a source of microwave, basically, from which you can see some light coming out or electromagnetic radiations being thrown into the container, basically. So what is the principle behind heating through this microwave oven is, you have a source of microwave irradiation. Say, for example, it's happening from here. These microwave radiations go and strike every wall within the cage-like structure that the domestic oven has to offer. And these will establish what is called as a static or a stationary wave. After it goes on colliding, it'll have some pathway wherein it will collide. So there'll be some parts which will be hot spots, and there'll be some parts which will be cold spots within the microwave oven itself. You understand? It's not a uniform heating across. It's just that the microwave radiations are coming out. They go and strike individual walls and they get quenched. So they offer certain places where there is intense microwave that is observed, certain places where the microwave radiations don't even penetrate. That is the reason why you need a turntable. The turntable is then going to help you in achieving heating of all the parts. So you tend to rotate the food material or the container in which you've placed your article, and as it rotates, it keeps absorbing microwave radiations, right? Now, why is this design not suitable to perform an organic reaction? Now, in an organic reaction, many a times we use solvents, and solvents usually have low flash points. So if they have a low flash point, they are not very well behaved to large differences in temperature over a short span of time. So if you use organic solvents inside this domestic kind of a microwave, as it rotates and comes in contact with a hotspot, microwave hotspot, it will get intensely heated over a very small period of time. And then it moves out, then the heating is stopped. So you're repeatedly making it go through pulses of getting heated at a very fast rate and then cooling it. So this, usually leads to buildup of partial pressure, vapor pressure of the solvent. And this buildup in vapor pressure eventually leads to explosions. And there are large examples of explosions that have happened when we use domestic microwave to perform organic reactions. And that is the reason we have a design like this of a microwave reactor, in which the RB flask, which goes here at the center, and it also has mechanism to monitor the pressure. If at all the pressure goes beyond a certain permissible limit, then you can have some safety feature in your microwave reactor, that it can cut off the microwave source completely. So all these attachments are also included. But basically the RB flask, which is sitting into this cavity, does not rotate. Okay. And the microwave radiations begin from one end and go through in a circular fashion. So it is uniformly heating all the surfaces of the round bottom flask, which is placed at the center of the microwave reactor. So you don't require the turntable over here, because you are not creating some localized hot spots and cold spots there, right? That is one advantage. The second advantage is you have something called as a power knob in your microwave, right? So whereby you could say that irradiate my food with 800 wattage power or 600 wattage power or 500 wattage power, etc. As you go on changing the power of microwave, your domestic microwave does not have the capability of tuning the strength of microwave radiation. So what it just does is, if at all you keep full power at 800 watts, then it will pulsate the microwave radiations. If for 1 minute you're keeping the microwave on, for about 50 seconds, it will keep the microwave radiations on. Okay, that would give an average power of 800 watts. Right? But it's not a uniform constant power being supplied. Okay. Whereas when you drop the power to 600 or drop the power to 400, what is happening? The same source with the same power will pulsate at a lesser frequency. So you will give a pulse of 5 seconds, then you would do a stop for 10 seconds. Then you would give another pulse of 5 seconds, stop for 10 seconds. So the average power that is delivered over a span of 1 minute then happens to be 600 watts. Again, needless to say why this doesn't work with commercial microwave reactors in which you want to do microwave reactions, because organic solvents again are not well behaved to such a drastic change in your temperatures or rate of heating and rate of cooling. Okay, and that is the reason your conventional microwaves domestically that is used cannot be used to perform microwave assisted reactions. We've learned it the hard way. Actually, a large number of accidents have happened in the past by using domestic microwave ovens to do organic reactions. So nowadays we have these safety instruments in place that can help us in doing some safe organic synthesis using microwave. Okay, so that brings us to the applications of microwave synthesis. You can talk about threefold application of microwave assisted synthesis. One of them is wherein you use water as the solvent to do microwave reactions. Okay, and that can help you in making the process green in two ways. One is you're using an energy efficient design by using microwave. You're using water as a solvent, whereby water is considered a green solvent. Another type is you could use organic solvents which are high boiling. Of course, we don't use low boiling organic solvents because the buildup in vapor pressure is going to be quite a lot when it comes to microwave interacting with these solvents. So usually the solvents used are like nitrobenzene, chlorobenzene, etc., whose boiling points are quite high and hence their vapor pressures are a little low. The third way is to do microwave reactions in the absence of a solvent. So I could do microwave reactions just by mixing two reactants together, placing it inside the microwave, and I could end up getting the products at the end of the reaction. Or the last way, which is becoming quite popular, is wherein I impregnate a solid support with the reactants, and the reaction happens on the solid support itself. So solid supports that are available are like that of alumina or silica, and sometimes the support is also coated with certain other ionic compounds like potassium fluoride, etc., which can help in efficient absorption of microwave radiations. Large number of examples are available in literature. One of them is N-alkylation. You could do alkylation reactions between chloroalkanes and piperidines using microwave. You could also do them on silica as your support. Within 6 to 10 minutes, we get almost quantitative yields in majority of the cases. You could also do S-alkylation, alkylation at the sulfur using potassium carbonate. On alumina, in about 4 to 10 minutes, you can get as high yields as 90% and above. The advantages, of course, are rapid and homogeneous heating when you're doing it on the solid support. The excess reagents are just washed away, so your purification step is simplified. You take the silica solid support and just wash off with some solvent which will remove your byproducts, and then give it one washing with the solvent which can selectively remove your desired product from the surface of silica, and that's how you can get your product solidified after you evaporate the solvent. And of course, needless to say that it's a quicker method, and sometimes it offers an easier route to access the product. But these are the examples that are given in the Lancaster book as well. The first is an example of a biphasic reaction in which this quaternary ammonium kind of a compound is treated with water and chloroform. Okay, so because the compound is polar, it will dissolve in water. So you will have the compound being present in water, and because water is a very efficient microwave absorber, in that 1 minute of microwave irradiation, water will become really hot. And because of the heat that is transferred efficiently, you would have the compound showing Hoffman elimination sort of a reaction. This Hoffman elimination leads to formation of alpha beta unsaturated kind of a compound. And this compound, because it no longer has the quaternary ammonium kind of a group, its solubility in water is very, very low. So it will eventually move across the phase boundary into chloroform. The advantage of this biphasic system is water is a very efficient microwave absorber, whereas chloroform is not that efficient a microwave absorber because of differences in polarity, basically. So water goes to extremely high temperatures in that 1 minute of microwave radiation, but chloroform only goes to about 48 to about 50 degrees Celsius. Right? So you could do efficient organic synthesis whereby you get as high as 97% overall yield for this transformation. Right? Other examples are converting amides to carboxylic acids, in which conventional methods require refluxing for 1 hour to get a 90% conversion, but whereas in microwave method, in 7 minutes we can get greater than 99% conversion. You can convert primary alcohols into acids directly by using 30% hydrogen peroxide in the presence of microwave, and sodium tungstate as another oxidizing agent over here. Or else you can also convert these amines into their N-acyl derivative using a solid support like silica, SiO2. Some other examples are conversion of secondary alcohols into the corresponding ketones by using sodium iodate on silica, or some aldehydes can be converted into the corresponding carboxylic acid using microwave.